Hello everyone, welcome to the fourth lecture of vibrations and waves. So far we've been looking at harmonic oscillators with and without damping. Today we're going to add a driving force to the system. We start with a spring. So we have a spring with a constant K and mass M. There's a spring force. This is the relaxed length of the spring. We also consider damping. So there is constant V in the system. We can already define V over M as gamma, and K over M as omega 0 squared. We add the driving force here, F0 cosine omega t. And now we write the Newton's second law, F equals ma. So m x double dot equals, what do we have? We have the spring force, so we have a minus k. We have a resisting force. I remind you that is a b times v, so it's a minus v times x dot. And we have the driving force F0 cosine omega t. Let us divide by m and substitute gamma and omega 0 squared instead of the k over m and v over m. What we get is x double dot. I'm going to also move the forces, the resistive force and the spring force to the left side, and just leave the driving force on the right side. So we have x double dot plus gamma x dot plus omega 0 squared x equals F0 cosine omega t. Divide by m. Alright? Now we move to the complex plane. We have z double dot plus gamma z dot plus omega 0 squared z equals F0 over m, and that would be e to the power j omega t. This is the equation that we would like to solve. We have a trial function z, some amplitude, e to the power j, and here I'm going to write omega t minus delta. You could write plus alpha, you could write plus phi, doesn't matter. There's a reason why I write it this way, and you're going to find out soon. But it's very important now to understand why I use this omega here. The same omega from the driving force. Okay, you can make it clear. This is the same omega from the driving force. Now, if I just give the spring a kick, it starts oscillating at frequency omega 0. Without damping. Now, even with damping, it doesn't matter if we have now a driving force. The initially the spring wants to do something else, maybe it wants to oppose my driving force, but if you give it enough time, the system eventually would start oscillating with this omega. So it's important to understand that in the solution, the trial function that we're putting, why we're actually using this omega here from the driving force. Okay. The meaning of delta is a phase angle, and what we're looking at is the steady state solution. So at the moment we don't care what happens initially, right, which is called the transient solution. We don't care what happens initially as we just start oscillating the spring with the driving force, but we want to see what happens if you give it enough time. What happens? That would be the steady state. So we're looking at steady state solution. All right. We plug this trial function here. Let's do that. What we get is minus omega squared plus, I'm going to leave the exponent for outside, okay, plus gamma times j omega plus omega 0 squared. We've seen this in the past. Now e to the power j omega t minus delta, and this is equal to f0 over m ej omega t. Notice that e to the power j omega t cancels from both sides. So we can write where is the a? You should have a factor a here on the left side, right? All right. So now I can write minus omega squared plus gamma j omega plus omega 0 squared times a. I get rid of this part here, and I'm going to divide by e to the power minus j delta. So on the left side, this is what I have, and on the right side, I would have f0 over m, and then e to the power j delta. Right? I didn't want to have it with a minus sign. Well, what is this? This is f0 over m, and we're still in the complex plane. Cosine delta plus j sine delta. This is just the definition of the exponent from Euler equation. Alright, so far so good. Now, for this to hold, as we already seen, there should be two equations. One has to do with the real parts and the other one with the imaginary parts. So we can write two equations with two unknowns, omega squared plus omega 0 squared times a. These are the real parts. The minus is only for this omega. this has to be equal to f0 over m cosine delta. And that is why I turn this part into real and imaginary. Okay. Now the imaginary part here, which is gamma with gamma omega a. I'm dropping the j because it's on both sides. We have gamma omega times a, and on this side we have f0 over m times sine delta. This is f0 over m sine delta. It's easy to solve if you just square these two equations, because this will give you sine squared and cosine squared, and adding them together would give you 1. So if you solve that, what you would get at the end is the following relation for A, the amplitude, f0 over m divided by square root of omega 0 squared minus omega squared, everything squared, plus omega gamma squared. Tangent delta equals omega gamma over omega 0 squared minus omega squared. Let's check this. That should be fine. Move it. Alright, so the now we go to the real world. So x equals the real part of z. X is a cosine omega t minus delta. This is the solution, and we want to discuss this for a while. First, notice that here we don't have the two adjustable constants as we had before, as the amplitude and the phase. When the system was free, we could decide at which point we put it, right? We can pull the spring further away, so we can choose A, and we can also give it a push, and we can decide both the phase and the amplitude. We have no longer that flexibility here. We don't have these adjustable constants. A is already given, it's given here, and delta, and it's not something that we can adjust based on the initial conditions. It's just as if the system has lost its memory. And we would expect that, actually, because we were talking about a steady state. What happens at the very beginning, it's not important, really. We wait enough time and we see what happens later on at the steady state. So the amplitude is dictated by the force, the driving force, and the mass, and of course the spring constant and gamma. But it's no longer a matter of an initial condition. Regardless to where you start, this is what you end up with, and the same with the phase. So the system has lost all of its memory. So A follows immediately from f0 omega and omega 0, and delta follows from gamma and omega 0. But you see that gamma is down here, And that is important because this is what you would expect. Gamma down here means that if the resistive forces are very large, then you would expect the amplitude to be smaller, right? So this is the place where you would expect it to be. Now let's try and analyze this solution that we derived. Now suppose that we apply a force F0 with a frequency which is very small, close to 0. Which means there's always an equilibrium between the spring force and the driving force. And so all the time there is that equilibrium between the spring force and the driving force. So in that case, I would predict that if omega is very small, right, is tending to 0, then the amplitude should behave like F0 over K. Because there's an equilibrium between the spring force and the driving force. And you can see this now here. If omega is tending to 0, then let's do it. If omega is tending to 0, then A equals, so we're looking at the limit where omega is tending to 0 of F0 over M divided by square root of omega 0 squared minus omega squared plus omega gamma squared. So we end up with F0 over M, and here we have omega 0 squared, which is simply K over M, and this is what we get, F0 over K. Exactly what we predicted here. So what is the phase difference then? Phase difference would be 0. You can see that immediately here. So the tangent of delta would be 0. All right. Now let's take another case, and that's the case of resonance. Suppose now omega is tending to omega 0. What happens now? Well, if omega tends to omega 0, then A would be equal to F0 over M omega 0 gamma. And if you remember the quality factor that we talked about last time, we can also write F0 over K times Q. Because Q is omega 0 over gamma. Right? Put it here. Q is omega 0 over gamma. And delta would be tending to pi over 2. This is the resonance case. Now at resonance, the amplitude is Q times larger. There's a factor of Q than the case of extremely low frequency. What we did before was the case of extremely low frequency, and we found that the amplitude is simply f0 over k. But in the resonance case, there is a factor of q for that amplitude. So if the quality factor of the system is 10, you would expect 10 times the amplitude to be larger. If it's 100, you would expect 100 times larger amplitude in the case of frequency. Now what happens if we go for the third case, and that is when the frequency is very large, infinitely large. So if omega is tending to infinity, this is the case now, then the amplitude would tend to 0. You see this here immediately. If omega tends to infinity, the amplitude goes to 0, and delta would go to pi. In other words, the object is not following. The driving force is so fast that the object is not following the driving force. And the amplitude as a result is simply 0. Now you might think that the maximum amplitude is at the resonance, but that's not true. And I will ask you also to derive the maximum frequency, the frequency of the maximum amplitude. Let's make a drawing here. If this is the amplitude, this is omega. We say that if omega is very small, close to 0, then we tend to some amplitude which is f0 over k. And if omega is close to the resonance frequency, so this is omega 0, then we would have some q. Let me delete this part here, a bit confused. Some q times f0 over k. And what you would expect to have is something like this. And at a large frequency, it would tend to 0. The amplitude would tend to 0. This is the maximum amplitude. And this is the frequency, omega max, is the frequency of the maximum amplitude. Right? Note that omega max is smaller than the resonance frequency, the natural frequency. Let's make another drawing here next to it for delta. Right, in a similar way, this is omega 0, omega, now this is delta. Okay. Let's take this as pi, and this is pi half. When omega is close to 0, delta is 0. At this point it's pi half, and when it tends to infinity, it tends to pi. Let's see a video about a driven oscillator. Alright, now let's see how to find this the maximum omega max. So the frequency of the maximum amplitude. Omega max. Actually, I would like you to find that. So all you need to do is take the derivative, dA d omega, and put it equal to 0. And from there you can find that. I'm just going to give you the answer. Omega max equals omega 0 squared minus gamma squared over 2. Everything is square root. So omega max can be also written as omega 0 times 1 minus 1 over 2 q squared to the power half. So you see that in the case that q is extremely large, so basically effectively there is no damping in the system, in that case is when we would expect that the maximum frequency, or the frequency of the maximum amplitude, would be exactly the natural frequency of the system. All right. All right, so if we know Q now, we can find the difference in percentage, for example, between the W max, the omega max, and omega 0. Let's just take some numbers to have a feeling of physical systems. So the A max would be F0 over K times Q over 1 minus 1 over 4Q squared. So Q, if Q is 5, then omega max over omega 0 is 0.99. So it's less than 1% difference. It's very close to the natural frequency, but it's not there. And in this case, you can also look at A max over A0. By A0 here, I mean F0 over K. Right? In this case, we will have a difference, a factor of 5.30. So the maximum amplitude would be 5 times larger than the amplitude in the case of very low frequency. Yeah, I would suggest that you take some time to study the figure in your book, figure 4.9 in French, right? Right, do you see that far? Yes, French. Take a pendulum now. So we've been dealing with a spring. Let's take a pendulum. You see this? Pendulum. This is the pendulum with length L and mass M. And we want to drive this pendulum right and left. So we drive this pendulum with theta, distance theta, displacement theta now. Not a force, but displacement, which is some constant cosine omega t. Right? This is a displacement now. So I'm holding the pendulum and I'm moving it right and left. I'm displacing it, so eta is the displacement here. So after some time, I can see the pendulum maybe here with some angle, theta. And this is exactly the, just not to confuse you, this is exactly the, this is eta, this is the displacement. And this is my x here. We know we have mg, and we have a tension, tension T, we have mg here. We have two components here. This is T cosine theta, and this is T sine theta. T is almost mg. That helps us a lot. Okay, so we make that assumption. And we also use the same notation as before. So gamma is B over M. And omega 0 squared G over L. Okay, this is the resonance frequency. All right, let's write the equation. F equals ma. We have the resistive force as before. Now we have mg sine theta in the x direction, right? This is mg sine theta, the minus sign. Now you need to be careful here because sine theta now is a function of eta here. So sine theta is x minus theta over L. So we can write now mx double dot minus equals minus bx dot minus mg x over L for the first, and the second would be with a plus sign, which is plus mg over L times eta. The eta is eta 0. You can write that down already. Cosine omega t. Okay, let's make some order now. X double dot plus gamma x dot plus divide by m, this is g over L, and that is omega 0 squared, okay, omega 0 squared times x. We're going to leave as before the driving force on the right, so we divided by m, there's a g over L here, so we can already write omega 0 here squared, and then eta 0 and cosine omega t. And this is the equation. See, every time that you get to this point, you've managed to translate the problem from the physical problem into a mathematical problem. But this is just as before, right? So we've solved this already. It is as before. I can write now A is omega 0 squared eta 0 over square root of omega 0 squared minus omega squared minus omega 0 squared, everything squared, and then plus omega gamma squared, and tangent deltas is as before. Now I want you to take a moment and really, without looking at the equations, I want you to think. Let me bring the pendulum. I want you to think what happens if when omega equals 0. So the frequency is very, very small. What does that mean? We want to find A and we want to find delta, right? Now, without looking at the equations, just look at the physical problem here. Now, omega equals 0 means that the driving force, which is my hand, is basically moving so slowly. So all the time there is that equilibrium, right? So the amplitude A is basically, see, I'm moving quite slowly. I'm trying to do a little bit faster. So all the time, so I've moved already, the amplitude A is equal to eta 0. Okay? And the delta would be 0. If I drive it at the resonance frequency, then what you would expect to happen, just as before, you'd have that amplitude now, the same amplitude that we had with that eta 0, right, when I did it very slowly, but with a factor of q. So if this has a q factor of 5, and the amplitude was eta 0, now it would be 5 eta 0. So it would go really large. You see the movement that I would be doing in my hand, you're gonna see shortly, it would be very, very small, but yet this would bounce from side to side with a very large amplitude. On the other hand, if I drive this very fast, then the object wouldn't even have the time to understand that I'm moving it. So it just, the amplitude, it won't follow, the object won't follow. The amplitude would be 0. This is what we expect. Let me write this down for you, and then we make the demonstrations. All right, let's write it down here. So we have the 3 cases. The first one, when omega equals 0, then the amplitude would tend to eta 0, and delta would be 0. The second case is when omega tends to omega 0. In this case, the amplitude would tend to q times eta 0, and delta would be, just as before, pi over 2. And in the third case, if omega is tending to infinity, is very large, A tends to 0. And delta tends to pi. All right, and the steady state solution, just to complete the solution here, would be the same, A cosine omega t minus delta. This is the steady state solution. All right, let's look into this. Let's do the first part, first demonstration. It's not gonna be very exciting. Okay, I'm gonna start. I've started. It's quite boring, I know. But you see, it's just the object have enough time to follow. So in every moment in time, the object is following and it's just moving with this, the amplitude is eta 0. I can also try and go to the opposite direction, maybe a little bit faster. All right. Okay, don't fall asleep. We are going to do now the case with the high frequency. So I'm doing the third case now. A high frequency, so basically I'm gonna move my hand from side to side very fast. And what you would see that the amplitude here should be very, very small. Let me first try and hold it. So I'm moving from side to side. I'm even moving now quite a lot, right? You can see my hand moving from side to side, but this is just almost jumping in place, right? The jumping is a different physics, but it's almost jumping in place, right? So my hand was going something like that, and this would just be still in place almost. Now let's go to the resonance. The resonance case, the second case. Once I hit resonance, you would see. Yeah, you should try it actually. You can feel it in your hand. Once you hit resonance, it's amazing. You just give it a very small displacement, right? So the driving force or the driving displacement now, right, is very small, and it would just bounce from side to another. Let's see this. Okay. Ready? Let's go. Let me just try to find it. Here we go. All right. I'm on resonance now. You see, it goes. I'm almost not moving my hand. You see how little my hand is moving from side to side, and the tennis ball is moving quite a lot from side to side. Look at this. Look at this amplitude. All right. So now to conclude, let's stay on this cam. To conclude, we discussed here the resonance case of one object, and that is related to one single frequency. So if I'm taking the tennis ball, there is a specific frequency, right, it's omega 0, that I have to move my hand with to hit resonance. There is one single frequency because there is one object here. If we had a second object tied to it, then there would be two frequencies that you can excite the system for resonance. The resonance subject is quite interesting subject, and there are so many different types of resonances that you probably are witnessing in your daily life even. When you talk about resonance, for example, in your daily life, you might think about when you're driving a car and you're accelerating, you're slowly accelerating, and the window is open. At some point you get to the point where the you can feel some very uncomfort feeling in the ears and in the and that is because the car is entering resonance. So you have resonance, and you can feel that, and that is bothering you. One example of resonance from the daily life would be also the washing machine, for example. As it accelerates, at some point it passes through resonance, and that's where things start really shaking. Now, if the manufacturers want their product to survive, then normally they would pass that point quite fast, and then as it turns faster, then it's no resonance anymore. So it's really when you get close to that natural resonance, natural frequency, is when things start to resonate, and the amplitudes start to become very large. The radiators, sometimes you're sitting and you simply hear the radiator start with making these large sounds, and you have to go and adjust the flow rate in the radiator. If you play with it a little bit, the flow rate changes, and as a result you move away from the resonance frequency, so that sound goes away. I have an example here, a glass of water. There's a glass of water, same thing. So if I let's see if I can do it with this cam. Let's try holding it. I never did it like this before. Cheers. So if I rub the sides here of the glass, that should excite all kind of modes. We're gonna get to this subject in depth. But one of these modes that you would be exciting would be the resonance frequency. As a result, the whole thing would start resonating at that resonance frequency. So what you would normally hear very gentle from other frequencies, suddenly the amplitude now is amplified. This is much larger than the others, right? As a result, you hear that above all the other frequencies. Let's try that. All right, I think you get the picture. All right, so yeah, finally I want to conclude the lecture by the following videos that I'm going to put. So until next lecture.
Perhaps you've seen a video like this one that seems to show the waves present when guitar strings are strummed. In reality though, guitar strings vibrate predominantly at their fundamental mode. The wave effect that we see is the result of how the camera's sensor forms each frame. Instead of taking snapshots, the camera progressively scans the data across the sensor. Since the scanning frequency and vibrational frequencies are mismatched, this can lead to the appearance of standing waves. But what does a vibrating guitar string actually look like? To see this, I assembled a strobe light with some parts I had laying around. A simple program then allows me to dial in any frequency on the fly. The purpose of the strobe light is to freeze time without needing an expensive high-speed camera. Things get rather interesting when the strobe frequency is matched to some periodic motion. In this example, the scene is only illuminated at the peak amplitudes. This actually happens so fast that we see a wave apparently frozen in time. If we offset the frequency just slightly, we can get the appearance of slow motion. One neat result is that we can now use the strobe light to tune a guitar. When the note's a little flat, like in this case, the string moves slowly, but as we get closer and closer to the target note, that motion ceases. Though the fundamental mode dominates, there are other modes present on any vibrating string. We can explore these with a simple cotton string fixed at one end and attached to a speaker on the other. In this case, the strobe is flashing at twice the frequency of the string resonance. If we match the strobe frequency, we see the wave in only one position. there actually are higher frequency modes that we can isolate by progressively decreasing the string tension. These are called overtones of the fundamental, and we can see them without changing the strobe frequency because they were always integer multiples of the fundamental. Resonance is a property of all materials, and the wine glass is a classic example. The wetted finger trick induces this resonance, and we can see it by carefully matching the strobe light. Now, I wanted to shatter this wine glass, and to do that I needed a hammer. I needed science. After grabbing some science, I recorded the tone, brought it into MATLAB, and did a Fourier analysis to find the dominant frequency. Once found, we can verify our work by listening to the two tones. Then it's just a simple matter of cranking up the volume. Wow, that was neato. It's not at all surprising that the glass shattered when you consider the fact that this glass was vibrating at over 400 times a second, and the amplitude was significant as we could see in the video. Liquids will resonate too, and because they have more degrees of freedom than a simple string, they accordingly have more ways in which to resonate. Things here do get much more complicated, and I even have a former colleague that spent an entire PhD studying droplets like these. But it's still interesting to tinker in seeing how changing the material properties changes the resonance. For example, like changing the tension on the string, we can change the size of the droplet, and in this way we affect its resonance.
I'd like to show you an example of levitating small objects with sound waves. Let me just remind you how a loudspeaker works. It's just a diaphragm that repeatedly pushes on the air, producing high pressure waves that move away. And that's what we have here with this little gizmo. It does the same thing, except it's at a very high frequency, 28,000 hertz, which is way above our human hearing range. So these sound waves move upward, and up above I have a glass plate which is going to reflect the sound back down again. And when the distance between the glass plate and the loudspeaker is just right, then those sound waves that are moving down will interfere constructively with the sound waves coming up and give us regions of high pressure and low pressure which don't move around. They stay in one spot. And it's in those high pressure zones that I'm going to try to levitate a small ball. So let me turn on the power, and even though I can't hear it, I'm still going to use ear protection. As I said before, the distance between the reflector and the loudspeaker is just right. If I change it, and which I'm going to do, you'll see that this standing wave disappears and the balls are no longer suspended there. We've now set up the little loudspeaker and the reflector in front of this mirror, which is part of our Schlieren optic setup. And the purpose of that is to be able to actually see where there are regions of high pressure and low pressure in the air, especially the air between the reflector and the loudspeaker. So let me turn up the volume, and before I do that, I will put on my protective hearing. And if I adjust the height of the reflector, there's a point at which you see bands of white, light, and dark. This is the standing wave, and it only happens when the distance between the reflector and the speaker is some multiple of a half a wavelength. So every single one of those bands is a half a wavelength. If I go up a little higher, then it disappears again, but if I continue to go higher, then it will come back when I'm at another half a wavelength, a multiple of a half a wavelength away. Now, it's in these bands that I'm going to place the little balls. And you can see the little ball settles down where there's a bright band, and that is the high pressure area. And I know it's a high pressure because you see there's a white band right next to the reflector, which is where the highest pressure will be. If I, again, change the height, the standing wave goes away and the little balls will fall down.